Hi there. In today's video, we're going to be talking about solution stoichiometry. Anytime I talk about stoichiometry, I like to think about it in terms of it being chemistry math. And so what we mean by stoichiometry is that we're trying to use math and trying to use what we know about chemistry in order to determine how much of a particular compound or solution or gas or whatever, how much of things that we need to mix together in order to cause them to react, okay? And so within the context of general chemistry, at one point or another, we've discussed two different concepts. One of those concepts is dimensional analysis. And dimensional analysis, we typically use this when we're looking to convert one measurement from one unit system into another unit system. Think about converting 3 feet into 36 inches. It's the same measurement, you're just describing it in two different ways. The other thing that we really use a lot in any kind of stoichiometry or solution stoichiometry is we use the balanced chemical equation. And the balanced chemical equation is really important because it allows us to know what the recipe is for some reaction. It gives us the ratios in which one compound reacts with another, okay, in order to form some product. So the balanced chemical equation is crucial to what we do in stoichiometry. Now, this particular kind of stoichiometry that we'll talk about today is called solution stoichiometry. And so the reason for that is because it's always dealing with solutions. And so, you know, when we first kind of talk about stoichiometry, we usually consider what's called mass stoichiometry, where you're taking a mass of a substance and you're using the periodic table in order to allow you to go from grams of that substance into moles of that substance, doing some kind of dimensional analysis there using the periodic table. In solution stoichiometry, the dimensional analysis that we're going to do involves molarity. And molarity is defined as moles of solute, okay, the moles of the stuff that you dissolve, divided by the liters of solution, okay? And that having this idea of molarity is really handy because lots of times in chemistry what we're doing is we're pouring two solutions together. We're pouring two liquids together and allowing a reaction to take place, okay? Sometimes those liquids we're pouring together are neat liquids, but most of the time what they are solutions where you have a tiny bit of some solute that you've dissolved into a bunch of solvent, a lot of times water, in order to make some solution, okay? So these are kind of all the tools that we're going to need in order to do some stoichiometry today. And there's kind of a roadmap that we can think about when we're thinking about stoichiometry. And the kind of the basis of that roadmap always involves kind of the balanced chemical equation. When we're thinking about stoichiometry, the idea generally is to get from some measured quantity of one substance to some measured quantity of another substance. And the basis of being able to convert from one substance to another substance mathematically involves the balanced chemical equation, okay? So the basis of stoichiometry is to say we're going to go from moles of compound A or solution A or liquid A or whatever. We're going to go from moles of that, okay, moles of A to moles of B, okay? And we're going to get that mole to mole ratio by using the balanced chemical equation, okay? On either side of that mole to mole ratio, once we've converted from moles of A to moles of B, the other two things that we need to do for stoichiometry involves dimensional analysis, okay? So we're going to start with some, say, I'll just call it a measured amount of component A. And we're going to do some dimensional analysis to turn that into moles of A. Then we're going to use the balanced chemical equation to go from moles of A to moles of B. And then finally, we're going to do a little bit more dimensional analysis to get us to a measured amount of B. Okay? So a lot of times, we'll say in mass stoichiometry, this measured amount of A or measured amount of B is grams. Okay? You're measuring some compound on a scale. You're using the periodic table to go from grams or mass of A into moles of A, and using the periodic table to go from moles of B into grams of B. Okay? In solution stoichiometry, what we're going to do is we're going to use molarity. We're going to use this idea that in a solution, there's a relationship between the volume of that solution and the moles of substance that are in that solution, right? Because it's a small amount of solute dissolved in some solution, okay? All right, so let's try some example problems, okay? And I'll write an example here. I think what we'll start with, we'll start with a balanced chemical equation that looks like this. Let's say we've got magnesium chloride, and that's a solution, okay, that can dissolve in water, and we're mixing that with silver nitrate. Oops, I really didn't need parentheses around there. That's also an aqueous solution. And then when we do that reaction, I'll run out of space here, so I'm going to come down here. When we do that reaction, what happens? This is a double displacement reaction. So the magnesium goes with the nitrate, the silver goes with the chloride. So we end up getting silver chloride, which is a precipitate in this reaction, and we get magnesium nitrate, okay? And that's going to be a solution. All right, and so this equation right now isn't quite balanced. We've got one chloride on the product side, 2 chlorides on the reactant side, so we'll need to put a 2 here, and that means we'll need to put a 2 in front of the silver nitrate, okay? And that's good because now we've got 2 nitrates on the left-hand side of this equation and 2 nitrates on the right-hand side of this equation, okay? So right now this equation is balanced. So this is our balanced chemical equation that we'll use in some problem, okay? And so a problem that we might ask, okay, we might say, okay, so how many milliliters of a 0.15 molar solution of magnesium chloride will react with 37 milliliters of a 0.21 molar solution of silver nitrate, okay? So anytime that we do stoichiometry, we got to figure out what's the question that's being asked. And the question is always going to be that we're trying to calculate some amount of a compound, okay? We're trying to calculate basically the measured amount of B, all right? And so we're being asked how many milliliters, a measured amount of, okay, MgCl2, right? So the question that we're trying to ask in this particular problem is how many milliliters of magnesium chloride, okay? And that amount of magnesium chloride is going to be equal to a measured amount of compound A, okay? So that's going to be equal to, what do we have? 37 milliliters of silver nitrate, okay? 37 milliliters of silver nitrate, all right? And so the first thing we need to do, we've got a measured amount of A, right? So this is our measured amount of A, okay? That's where we're starting with. So our first step is going to be to convert from a measured amount of A into moles of A, right? So how are we going to make that conversion? Well, we need some relationship between volume and moles of silver nitrate. Well, we've got that, okay? We've got this number right here, okay? We know that this silver nitrate solution has a molarity of 0.21, okay? That means there's 0.21 moles of silver nitrate in 1 liter of silver nitrate solution, okay? Well, we don't have a whole liter of silver nitrate solution. We only have 37 milliliters, okay? So the first step that we're going to actually do here is convert this milliliters into liters. We need to do that because we've got molarity, which is in moles per liter. Okay, so let's do that. Well, we know that we can do a little bit of dimensional analysis here. Okay, and we can say, well, there are 1,000 milliliters in 1 liter. Okay, that's going to convert our silver nitrate from milliliters to liters. And in fact, milliliters on the top and bottom will cancel. Then the next thing that we can do is convert from our liters of A, our liters of silver nitrate, into moles of silver nitrate. And we'll do that using this guy here. Okay? So we can say that there are 0.21 moles of silver nitrate in 1 liter of solution. Okay. Now we've got liters of solution on the top and bottom, so those units cancel as well. Okay. All right, so now we're in moles of A. So the next step here is going to be to convert from moles of A, moles of silver nitrate, into moles of B. In this particular problem, okay, magnesium chloride is our B, okay, is the B compound that we're trying to convert to, right? So if we look at the balanced chemical equation, we see that there's a 1 in front of the magnesium chloride and there's a 2 in front of the silver nitrate. That says that for every 1 mole of magnesium chloride, it takes 2 moles of silver nitrate, right? So this allows us to see what the mole-to-mole ratio is between magnesium chloride and silver nitrate. So I know that for every 2 moles of silver nitrate, okay, there's 1 mole of MgCl2, okay? So in this step, look what we've done. We've converted from moles of AgNO3 into moles of MgCl2. Moles of AgNO3 are on the top and the bottom of that equation, so they cancel. So right now, we are here in this roadmap, and our units are moles of magnesium chloride. Okay? I'm running out of space here, so I'm going to move back over here. But my next step is to multiply by another fraction. So I'll put my multiplication sign here, but I'm going to come back down here to write the next fraction. Okay? So the next step is to go from moles of magnesium chloride into some measured amounts of magnesium chloride. Okay? Remember, in the end, I'm looking for milliliters of magnesium chloride, right? So I'm looking for a volume. So do I have some relationship that allows me to go from moles of magnesium chloride to volume of magnesium chloride? Well, sure. I have this number right here, okay? I'm told that that magnesium chloride solution that I have has a molarity of 0.15 molar, okay? Remember, molarity is moles per liter, so it's moles of MgCl2 divided by liters of MgCl2 solution, right? So if I want to get rid of the unit moles of MgCl2, okay, I'm going to want to write my next conversion factor like this, right? Remember, this is my multiplication sign. I'm moving down here. I'm going to write that in 1 liter of solution, okay, of MgCl2 solution, there is 0.15 moles of MgCl2. Okay? So look what I did. I actually flipped the molarity over, right? It's actually 0.15 moles per 1 liter. I put the 0.15 moles on the bottom of that fraction. Why did I do that? Because I've got moles of MgCl2 on the top here. And now that I've got moles of MgCl2 on the bottom here, okay, those units cancel. And now the only units that I have left is liters of MgCl2 solution, right? And that's getting really close to what my original problem was looking for. I was looking for milliliters of MgCl2 solution. So I could do just a little bit more dimensional analysis, right? And say that in 1 liter, there are 1,000 milliliters, okay? So liters and liters cancel. And the only unit that I have left is milliliters of MgCl2 solution. All right. So I started with a measured amount of A. In this case, A was silver nitrate. Okay. I started with a measured amount of A. Okay. I converted that into moles of A, moles of silver nitrate. I converted from moles of silver nitrate into moles of magnesium chloride by looking at the balanced chemical equation, okay, and seeing that it's a 1:2 ratio. And then I converted from moles of magnesium chloride into liters of magnesium chloride, or volume of magnesium chloride, by using the molarity of magnesium chloride. Okay? So now that I've set all that math up, I can just do that math on my calculator, right? So I've got 37 milliliters, okay, divided by 1,000 times 0.21, divided by 2, divided by 0.15 times 1,000, okay? And so in the end, what I end up with is that in order to react 37 milliliters of silver nitrate, it will take, I'm going to just say 26 milliliters of magnesium chloride solution. Okay? And it's magnesium chloride solution that has a molarity of 0.15 molar. Right? So this is solution stoichiometry. It's really a lot like mass stoichiometry. In mass stoichiometry, what you would have done is started with a mass of A, used the periodic table to go to moles of A, use the balanced chemical equation to go from moles of A to moles of B, and then use the periodic table again to go from moles of B into mass of B. With solution stoichiometry, the real difference here is that we don't need the periodic table at all. Okay? What we're doing is using the molarities that we're given to allow us to convert from a volume of solution into moles of the solute of that solution. All right? Let me erase the board here, and then we'll try another one. All right, so now that the board is erased, I've written another problem here. And for this problem, what I thought we would do is kind of blend together solution stoichiometry with the maybe more traditional mass stoichiometry. Okay, so this problem here asks us how many grams, okay, of AgCl can be produced from 0.75 liters of a 0.21 molar solution of silver nitrate. Okay, so look what's happening in this balanced chemical equation here. We're taking two clear solutions and we're pouring them together. When we pour them together in the beaker or whatever, one of the products that we make is silver chloride. Silver chloride is a precipitate of this reaction. Okay, so you pour two solutions together, you get a solid. That solid is silver chloride, and it could be filtered out of solution. Okay, so this problem is asking us for the grams of that precipitate we could produce, given that we have a volume of one of the reactants. Okay, so we have to figure out what's the A and the B here in our roadmap, right? Well, B is always going to be the component that we're looking for some measured amount of, right? And so in this problem, we're asked how many grams, that's our amount, or our measurement, right? Grams of silver chloride. So silver chloride here is our B. So I'll write silver chloride. So silver chloride is what we're trying to get to, and it's grams of silver chloride. Where we're starting from is a volume of silver nitrate solution. And that silver nitrate solution has a molarity of 0.21. So our measured amount of A in this problem is going to be 0.75 liters of silver nitrate solution. Okay. All right, and so we need to be able to convert from that measured amount of solution into moles of silver nitrate. Well, how do we do that? Well, we've got molarity, right? Molarity, this 0.21 molar, molarity is moles of solute per liter of solution. So it's moles of AgNO3 per liter of solution. Well, we don't have quite a liter. We've got 3/4 of a liter, right? But we can use molarity. We can use this molarity of 0.21 moles per liter as our conversion factor to get us to moles of A, right? Moles of silver nitrate. Once we're there, we can look at the balanced chemical equation and see that the coefficients in front of silver nitrate and silver chloride are both 2. So it takes 2 moles of silver nitrate to make 2 moles of silver chloride, okay? So it's a, I'll just say a 2-to-2 ratio there, okay? And then finally, we need to be able to go from moles of B, or moles of silver chloride, into grams of silver chloride. Well, how are we going to get there? Well, we're going to use the periodic table, right? Because molar mass, what's on the periodic table, tells us the relationship between the grams of a substance and the moles of that substance, okay? So if you go to the periodic table, what you'll see is that silver has a molar mass of 107.87 grams, okay, per mole. Chlorine has a molar mass of 35.45 grams per mole, okay? And so, let's see, that equals AgCl has a molar mass of 143.32 grams per mole, okay? So that's what's going to allow us to convert from moles of silver chloride into grams of silver chloride. Let me erase that to get that out of the way. Let's remember that number, 143.32. I'll write that right here, 143.32 grams per mole. Okay? So remember, our original question here was to say how many grams of silver chloride are equal to 0.75 liters of silver nitrate solution. Okay? Our first step is to use molarity. Molarity is going to allow us to convert from liters of solution into moles of solute. And the molarity tells us that there's 0.21 moles of AgNO3 in 1 liter of AgNO3 solution, right? So that allows us to cancel liters of solution and liters of solution. So now the only unit we're left with is moles of silver nitrate, or moles of our A in this problem, right? Our next step then is going to be to convert from moles of A, moles of silver nitrate, into moles of silver chloride. Well, we know that for every 2 moles of silver nitrate that we react, we will produce 2 moles of silver chloride. Okay. Now, moles of silver nitrate and moles of silver nitrate cancel. Okay. The unit that we have left is moles of silver chloride. That's moles of B. And so our final step then is to convert from moles of B into grams of B by using molar mass. Okay. So we're going to say that in every 1 mole of silver chloride, there are 143.32 grams of silver chloride. And what does that allow us to do? It allows us to cancel out moles of silver chloride in the numerator and the denominator, so that the only unit we have left is grams of silver chloride. And remember, that's the original unit that we were looking for. Okay? So now that we have this problem complete, all we need to do is do the math. So let's give that a try. So we'll take our 0.75, we'll multiply that by 0.21. We can multiply by 2 and then divide by 2, right? And that gets us back to the answer before we did that, but that's okay. And then we can multiply by 143.32, okay? And that gives us our grams of silver chloride. So I'll go ahead and round that and say 23 grams, okay? So if we have 0.75 liters of a silver nitrate solution that has a molarity of 0.21 is provided that we have enough magnesium chloride, we can produce 23 grams of silver chloride. Okay. So this was an example of stoichiometry that used both the kind of solution stoichiometry and mass stoichiometry. Right? Remember, the only real difference here is what we use in order to convert from a measured amount into moles, okay, and what we use to convert from moles to a measured amount. So if your measured amount is a mass, then in order to get from that mass or grams into moles, you're going to want to use the periodic table and find molar mass, because that's what molar mass is. It allows you to convert from, or it allows you to know the relationship between grams of a substance and moles of a substance. If your measured amount is a volume of solution, then you're going to want to use the molarity of that solution, because that's what molarity is. Okay? It is a description of the moles of solute in a volume of solution. Okay? Molarity and molar mass, kind of, you use them the same way in stoichiometry. All right? So I hope this video was helpful. Stoichiometry, solution stoichiometry, mass stoichiometry, whatever, it takes lots of practice. And so for that, I'm going to produce another video with a kind of a digital worksheet that goes with that. And I'll post the link to that video and the worksheet in the notes section for this video. So if you feel like you could use some more practice, please hop on over to that and try some more problems out. I hope this video was helpful. I appreciate you stopping by. I'll see you next time.